1. Provide reagents that would affect the following transformations. Use the reaction menu provided on the resource sheet. So in this problem, we're given this original precursor molecule, which is an alkyl halide, and we're asked to identify which reagents it reacts with to transform into each four of these other molecules. And I think I'm just going to go in a clockwise direction, starting from this first top transformation. And I think we're just going to ignore this part that says use the reaction menu, because depending on which year or which semester you're taking the class, as well as who your professor is, you may not be given a reaction menu, and I think it's just better to know the reactions as they are. So I'm going to start with this first one up top, and there's two hints that point towards it being an E2 reaction. First, there's only one product that's formed, because keep in mind that in terms of products, they're all going to form one product, except that E1 and SN1 reactions are not differentiable. So when that happens, you can expect two different products to form. Second, the product is an alkene, which points to an elimination reaction. So we're getting rid of SN1, SN2 in our minds when we look at this product. So right off the bat, we kind of assume it's an E2 reaction, and I'm going to write that here. In an elimination reaction that's an E2 reaction, we require a strong base. And keep in mind that it's a base and not a nucleophile that we want, because a strong base is going to grab onto a neighboring hydrogen atom, and it's going to act as an acceptor of that proton. Nucleophiles are associated with SN1 and SN2 reactions because they attack the carbocation or just the carbon atom in general, whereas bases are quote unquote attacking or accepting a hydrogen. And that's an important difference we should keep note of. And for this problem, we just, for this reaction, this E2 reaction, we just need a strong base. So it could be anything that's like OR with the oxygen being anionic. So I'm just going to write OCH3 because I think that's pretty common reagent. And I'll show you the mechanism. So we're starting off with this molecule, this alkyl halide. It's a secondary alkyl halide. And keep in mind that with E2 reactions, it's a concerted reaction. So all of the steps happen in one go. Well, we don't have the leaving group just leave immediately first before the reagent comes into play. It's all done in one step. And in this case, remember that there's two hydrogens in this neighboring that are bonded to this neighboring carbon atom. And with elimination reactions, the hydrogen must be trans to the leaving group. So in this case, since the bromine is wedged, this hydrogen has to be dashed. The hydrogen that we accept for the space has to be dashed. So I'm going to represent both of these hydrogens that are bonded to this carbon atom as wedged and dashed. And this anionic oxygen is going to attack or accept this dashed hydrogen. And then this bond will break, and then it's going to push over to become an alkene or a double bond here. And then that's going to push this leaving group to leave. And you'll have an end result that looks like this. A byproduct of CH3OH, because remember that this oxygen atom is accepting a hydrogen as a base. And we're also going to have a leaving group of Br minus. And as you can see, this matches up with what we have here. So that's our first reaction reagent. For this second reaction we're looking at, going in the clockwise direction, we're transforming this bromine into a CN group. And keep in mind that the wedge turns into a dash, and this is really important because it's going to be a major hint as to what kind of reaction mechanism it is. So in this case, it's an SN2 mechanism, and there's two hints that hint towards it being an SN2 mechanism. First, we have the bromine is substituted with a CN, and this comes from NaCN, which, if you remember, it's a very strong nucleophile. And remember that strong things, strong bases or nucleophiles are associated with E2 or SN2 reactions, whereas the weak counterparts are associated with E1 and SN1. And second, there's an inversion of stereochemistry, which is characteristic of an SN2 mechanism, and it doesn't happen in SN1 because in SN1 there's scrambling of stereochemistry, and I'll show you why that this is an SN2 mechanism and why this stereochemistry is flipped. So we know that this is coming from NaCN and it's an SN2 mechanism, so I'm going to write that in as the reagent and as a note that it's an SN2 mechanism, and I'll show you the mechanism as for this reaction. So as with the previous reaction, we start off with the same molecule. It's a secondary alkyl halide, and we know that NaCN is ionic, so it's going to split into Na plus and Cn minus anions. We just don't care about the cationic ions because they're kind of not participating in the reaction mechanism. So because it's an SN2 mechanism, it's also a concerted one-step process. So rather than the leaving group just leaving first to form a carbocation, we're not forming a carbocation at all. That step is, we skip that step, and this instead this Cn minus is just gonna attack from the other side of this wedged bromine, and then this bromine is gonna leave. And because it is hindered on this top side, it can only attack from the bottom side, which is why we have inverted stereochemistry. And we get a product that looks like this. And then we also have, I guess, Na plus and Br minus as side products. And this matches up with what we're given in this problem. The third reaction in this problem has two products, and this immediately points it to being an E1/SN1 reaction because it's the only reaction in this unit that will give us two different products that are not differentiable. So I'm just going to go ahead and write down SN1, E1 here as a note. And I guess the next thing we have to do is decide on a reagent. Because E1 and SN1 are both affiliated with weak bases or nucleophiles, we can just choose something that's weak, both as a nucleophile and as a base. And we're kind of given a hint as to what we should choose because we see that this is the elimination product, right? Because elimination results in an alkene, and SN1 results in an alkane with a substituted leaving group. In this case, the substituted group is SCH3, and we can just kind of protonate it into CH3SH as a weak nucleophile or base. Because, as you remember, this is really similar to CH3OH or methanol, which is also a weak nucleophile/base. So I'm just going to write that down as our reagent, and I'll show you both of the mechanisms. So starting off with the E1 mechanism for this part of the problem, we start off with the same alkyl halide we're given as before, and because it's E1, it's not a concerted one-step process. So the leaving group is going to leave first, and we're going to have a carbocation. And then remember that this hydrogen is adjacent to this carbocation, and then this base, this weak base, the sulfur has these lone pairs that it's electronegative. It's gonna accept this hydrogen, and then this bond will break between the hydrogen and the carbon, and it's gonna push over here and form a double bond. So you're gonna end up with a result that looks like this. And we're gonna have Br minus leaving group as a side product. And this does match up with this first product that we're given. The second reaction that we can't differentiate between in this part of the problem is SN1. And this is a little bit different from the E1 reaction in that it doesn't form an alkene. So like the E1 reaction, the leaving group will first leave, and it's going to form a carbocation. But this next step is different, and if you remember that back to the first reaction I discussed or not the first reaction, the second reaction I discussed, it was an SN2 reaction, and it involves an inversion of stereochemistry. But in this case, an SN1 reaction will not create an inversion of stereochemistry, because as you can see, because the leaving group has already left, and we're just left with a carbocation, both sides, both the top and bottom side of the carbocation are relatively unhindered. So this sulfur atom, or this nucleophile, is going to attack equally from both sides. And we're just going to get something like this, where it's going to be scrambled. And I guess it's not really shown here. We're only shown this single line instead of this tornado-looking thing, or we're not shown both the wedges and the dashes. I guess they just did that to make it simple so that you can identify it as SN1 reaction. But just keep in mind that if the problem asks you to draw all major products, including both the RNS enantiomers of the SN1 product, just draw them as something like this and this. But yeah, that is the third reaction in this problem. The last reaction we're going to be looking at in this first problem is also an E2 reaction, and it's an E2 reaction for two different reasons. First, there's only one product that's formed, so it can't be E1/SN1 because those are indifferentiable for the purposes of this class. And second, the product that's formed is an alkene, which points to an E2 reaction. So I'm going to write down E2. And next, we have to choose a reagent for this reaction. And just like this first reaction, which I also identified as an E2 reaction, anything that's OR with a negative charge on the oxygen atom is fine. In this case, I'm just going to use the same strong base as the first reaction we looked at, which is OCH3 with the negative charge on the oxygen. And I'll show you the mechanism for this reaction. So we start off with the alkyl halide with bromine that's wedged, and we have this strong base, right? It's anionic, and since it's an E2 mechanism and not E1, it's going to be a concerted one-step process. And in this case, the difference between this product and this product results from the difference in which hydrogen was taken, which hydrogen was accepted by the base to form the alkene or the double bond. So in this case, it was the hydrogen to the left of, in this first case, it was the hydrogen to the left of this bromine group. But in this case, it's the hydrogen to the right of the bromine. So I'm going to resemble that, and keep in mind that there's actually two hydrogens, or actually three, and because there's three, one of them is bound to be the dashed stereochemistry, which is what's required for this reaction to work, because remember that the hydrogen and the quote-unquote leaving group has to be trans. And in this case, the strong base is going to accept this hydrogen atom, and then this bond will move over to create a double bond adjacent to it, and that's going to push this leaving group out. And we're going to get a result that looks like this. And we'll have ER minus and methanol, or CH3 OH as side products. And as you can see, this matches up with what we're given in this problem, and that's how you answer this question. 2. A secondary haloalkane can undergo both substitution and elimination reactions. In the boxes provided, indicate the major product or products of the following reactions, and then indicate which reaction mechanism, SN1, SN2, E1, or E2, the reactions proceed through. Finally, provide the IUPAC name for the starting material, including stereochemistry. So for this problem, I'm just going to go from left to right, starting with this reaction with water, and then I'll name it at the end. So we're going to start with the reaction with water, and we know that water is a weak nucleophile. So that's going to be characteristic of an SN1 reaction, because remember that SN1 and E1 are associated with weak reagents, whereas SN2 and E2 reactions are associated with strong reagents. This is because SN1 reactions take multiple steps, whereas SN2 reactions take one step, because the strong nucleophile in an SN2 reaction is strong enough to push the leaving group out on its own. So it doesn't require it to leave on its own beforehand, before it attacks the carbon atom. So it's going to be an SN1 reaction. And I'm going to show you the mechanism, and we can figure out the product from there. So we start off with a molecule that looks like this. It's an alkyl halide, and it has a methyl group attached to it as well. And we're reacting it with water, but since it's an SN2 mechanism, we disregard the water for now until the leaving group chlorine leaves. So you're going to get a carbocation intermediate like this. And immediately we should recognize that this carbocation can be rearranged to form a more stable carbocation. Because as you can see, this carbocation is secondary. It has 2 carbons adjacent to it, but this carbon that's adjacent to it is a tertiary carbon, because remember, the methyl group counts as a carbon, this counts as a carbon, and then this carbon that the carbocation is also counts as a carbon. And remember that the higher number, the more stable it is. So we can rearrange and hopefully try to get the carbocation to this carbon that's attached to the methyl group. And here, we know that we can move the methyl group over to shift the carbocation, but remember that carbon has 4 bonds, and we don't immediately see it on this line structure, but there's also a hydrogen that's bonded to this same carbon. And in this case, it's easier to move the lighter item than the heavier item. So instead of moving the methyl group, we're going to move the hydrogen, and it's going to shift the carbocation to the left. And actually, in this case, there's no stereochemistry because there's only 3 bonds to this carbon atom instead of 4, so we can't even assign stereochemistry. So I'm just going to represent it with a line. Now we can bring water back into the equation. And remember that the oxygen atom on water is partially electronegative, and so it's going to have that the partial negative charge that's attracted to this positive charge of the carbocation. So the oxygen of the water molecule is going to grab the carbocation, and it's going to bind to it and create something like this. Or I'll just draw it out in a more clear way. The carbocation is no longer positive, but instead the positive charge is shifted to the oxygen atom on the water molecule. Because remember that each step should have the same net charge overall as the next step, unless you're adding or subtracting new molecules. And actually, we can redraw this as 2 different intermediates, because now that we have 4 substituents to this carbon atom, we can actually draw stereochemistry. So we're going to have one with the methyl group being wedged and this water molecule being dashed. We're also going to have one where It's the opposite way around. Remember that in this problem, we have a lot of water molecules in solution. So we can bring another one down, and it's going to deprotonate this positive charge. It's going to act as a base and accept one of these hydrogen atoms, and then this bond will break, and it's going to bring its electrons back to the oxygen. So for this first intermediate, we're going to have something that looks like this. It's an alcohol with the OH group that's dashed in the back. Similar thing is going to happen with the other intermediate. The water is going to accept a proton from this molecule, and then this bond will break between the hydrogen and the oxygen, and the oxygen will become neutrally charged. And again, we're going to have an alcohol, but this time the OH group is going to be wedged, and the methyl group will be dashed. So these will be your two major products of this reaction. So I'm going to go ahead and draw that in. The second reaction we're going to be looking at is this molecule, this alkyl halide's reaction with NaOH. And immediately we should recognize that NaOH is a strong base. So it's actually going to dissociate into Na plus and OH minus ions because it's an ionic compound. And we're just going to disregard the Na plus ions because they're not really going to participate in the reaction. And because NaOH is a strong base, not a weak base, we know that it's an E2 mechanism. Because remember that SN1 and E1 are associated with weak bases or nucleophiles, whereas SN2 and E2 are associated with strong bases and nucleophiles. In this case, we're only given E1 or E2 to choose from, not SN1 and SN2 as well, so we know it's E2. And I'm going to draw the mechanism for this reaction so we can determine the product of this reaction. Again, we're starting off with this alkyl halide that has a chlorine atom and a methyl group attached to it. And we know that NaOH splits off into Na plus and OH minus ions, and we disregard the Na plus ions. And in this case, because there's no hydrogen that can actually react in this E2 mechanism, because this methyl group is wedged, so this hydrogen has to be dashed, we're actually going to do another step where, if you remember the properties of single bonds, they have freedom of movement and freedom of rotation. So they can rotate. And then we're going to get something that looks like this. With this chlorine group changing stereochemistry to a wedged, and this hydrogen is going to be dashed. At the same time, this methyl group is going to stay wedged, and the hydrogen here is going to be dashed. And now we see that this chlorine and this hydrogen are trans. They're opposite stereochemistry, so this reaction can proceed. And we're going to bring down this OH minus ion from before. And remember, it's E2, so it's a one-step concerted mechanism. So in this case, the OH anion is going to act as the base. It's going to accept this hydrogen as a proton. And in the meantime, this bond is going to break, and it's going to shift over to make a double bond or an alkene here. And that's going to, as a result, push out this leaving group, which is the chlorine, and it's going to break off the bond. So we're going to get something that looks like this. And we're going to get H2O and Cl minus as a side product. So I'm going to draw that in. And that is the major elimination product for the reaction with NaOH. Now we can name this precursor molecule. So we know that there's two stereocenters, which is indicated by this wedged methyl group here and this dashed chlorine. And the first thing we need to do is determine whether these are S or R configurations. So let's start with chlorine, as it's going to have the higher priority for numbering, as you will see later on. So obviously the chlorine is going to be the first group. The next largest group would be this left side with this methyl, and then the rest of the parent chain. And then finally, the least priority substituent for this carbon atom will be on the right side of the carbon. And as you can see, this goes in a clockwise direction, so you would think that it's R, because as we know that clockwise corresponds with an R configuration, whereas counterclockwise is corresponding to an S configuration. But actually, because this chlorine atom is in the back, so there's a hydrogen in the front, it appears as an R configuration, but is actually an S configuration. So I'm just going to write that here. The next stereocenter we want to consider is this methyl group. Here, it's pretty simple because the methyl group is in the front because it's wedged. There's a hydrogen in the back, so we don't have to go through that whole mental gymnastics. We just have to label the priorities in order and just figure out from there. So obviously, the first priority will be this right side of the carbon, because remember that chlorine has a higher molecular weight than carbon, which is the next atom in each of these, on each side of this carbon atom. So we're going to assign number 1 to the chlorine side. Next, we have this left side and then this methyl group that's wedged. Obviously, the methyl group is just a single carbon. This side has 3 carbons, so it's going to be a greater molecular weight. So this side will have the second priority, and then the methyl group will have the third priority. And in this case, we also see that it goes clockwise, and that corresponds with an R configuration. And we're just going to leave it as R because in contrast to the previous stereocenter we considered, this one doesn't have the hydrogen in the front, so we don't have to flip the R and S configuration. So we just leave it as R. So I'm going to erase all of this, and I'm just going to label this one as R. The next thing we need to do is identify the parent chain and name the substituents. So there's 2 ways we can name the parent chain. We can either number from left to right or from right to left, but I think we want to name it from right to left because remember that we want all of the substituents with the stereocenters to have the lowest number priority possible. And in this case, starting from the right side will help us accomplish that. Another note that I want to make is that when we're given multiple substituents or stereocenters with substituents, we want the halogen group to have the lowest number possible. And in this case, so basically we just want the chlorine to have a lower number than the methyl group if that's possible. If it's not possible, it's okay. But in this case, it works out nicely because if we number from right to left, the carbon that's bonded to the chlorine will get the lower number anyway. The number is 2 instead of 3. So now that we have established the R and S configuration, and we've also established the numbering of this parent chain, we know it's a hexane because it has 6 carbons, we can start with this first part of the name, which is the R and S configuration. when there's only one stereocenter in a molecule, you don't have to number the R and S configuration at the start of the name, but since in this case we have two different stereocenters, we do need to number them. And we just go in numerical order from the smallest number to the largest number. In this case, we're going to start with 2, which corresponds to this carbon that is attached to a chlorine. And we previously established that it's an S configuration. So I'm going to write 2S, comma, and then for the second part of this, we just write 3R because we established that this carbon stereocenter is R configuration, and we numbered it as the third carbon in the parent chain. The next thing we want to do is name the substituents. So we want to go in order of numbers, just like we did in this first part. And this works out nicely because chlorine will just naturally have the lower number of 2. And remember that it's not 2-chlorine, it's 2-chloro for the prefix of this name. And then there's another substituent here that we established as a methyl group, and it's at carbon number 3, so we're going to write 3-methyl. And since this is a 6-carbon long parent chain, and it's linear, it's not cyclic, we're just going to write hexane. 3. Predict and draw a product of the following reactions. Note, providing mechanisms is not required for full credit, but can be used in assigning partial credit if the correct product is not shown. For this problem, I'm going to divide it into 3 parts, A, B, and C, because I think it's useful to organize it this way. And I'm going to start with A, and we're given this alkyl halide as a starting material, and then we're asked to identify what kind of product results from reacting this precursor molecule with 2 sets of reagents. So I'm going to start with the left reagents, and in this case, I think the first thing we should probably do is identify what type of reaction mechanism it is. And by that I mean E1, E2, SN1, or SN2. And we can already eliminate E1/SN1 in this case because remember that E1 is associated with weak bases and SN1 is associated with weak nucleophiles. And when we think of the term weak, we usually think of neutral or positively charged reagents. In this case, this reagent is negatively charged, and just as a side note, the Na plus ion doesn't really matter because it's just there to be like the salt of a conjugate base, but when you put it in solution, it just dissociates and does not participate. And I'm just gonna cross that off here too. And back what I was saying, CH3S- is strong. It's gonna be either a strong base or a strong nucleophile because we see that it has a negative charge. And that makes it strong because the negative charge is going to be attracted to the partial positive charge of the carbon atom. And in this case, we know that it's a polar A product solvent because it doesn't have a hydrogen bonded to this sulfur. And so we know that it's going to be an SN2 reaction because remember that SN2 is associated with polar A product solvents, whereas SN1 is associated with polar product solvents. And if it was polar product, it would be something like CH3SH, where you can see that there's a proton or like the hydrogen atom bonded to the sulfur, and that would make it that would indicate it's probably an SN1 reaction. But since we don't see this hydrogen anywhere, it's not going to be an SN1 reaction. So now that we've identified it as an SN2 reaction, we can go ahead and draw the mechanism and figure out the product of this reaction. So we're starting off with this alkyl halide, and I'm just going to draw it here. And we have this bromine, right? And remember, we're reacting it with CH3S- and Na+, which is an ionic compound, and this Na+ doesn't really do anything in this reaction, so we can just kind of ignore it for now. And as we previously established, this is an SN2 reaction, so it's going to be one step and concerted. So what that means is that this nucleophile is going to attack this carbon where the bromine is attached to. And keep in mind, it's actually going to be the sulfur atom that's attacking it because it has the lone pairs and the partial negative charge, or in this case, the full negative charge. And that's going to be enough to push this bromine off of the molecule. So it's going to be a leaving group and it's going to leave. And you're going to get something that looks like this. And remember that in an SN2 reaction, we're having inverted stereochemistry, and the reason is because this is a one-step mechanism. It's not multiple steps. The leaving group stays on until this the reagent or the nucleophile attacks the carbon and brings it off. And because the leaving group stays on until that happens, you can see that in this case, this top side with the wedged bromine is blocked off. So the nucleophile, the CH3S minus, cannot attack from the top. It has to attack from the other side, the bottom. And that's why we have inverted stereochemistry when it comes to SN2 mechanisms. So that's going to be our product, and I'm going to draw it over here. For the second half of this first part of this problem, we're given a similar reagent except the S is substituted with an oxygen. And in this case, we can recognize this off the bat as a strong base, which is associated with E2 reactions. And this is because CH3O minus looks remarkably similar to CH3OH or methanol. And if you remember from the review sheet that your professor probably gave you, CH3OH is a common reagent for E1 reactions, so its conjugate base is going to be stronger, which is this, because it's losing a proton or hydrogen atom, and therefore it's going to be an E2 reaction. Because keep in mind, like I said before, that weak bases are usually neutral or positively charged, and strong bases are usually negatively charged. So that's how we determined that it's an E2 mechanism. And now that we've determined that it's an E2 mechanism, we can go ahead and draw out the mechanism and draw out the product as well. So we're starting off with the same precursor molecule, this alkyl halide with a bromine group. And this time it's an E2 mechanism, so it's still going to be a concerted one-step mechanism. So we're not going to do anything with the leaving group yet. We're going to just first react it with the reagent. And remember that Na plus is kind of just irrelevant. We don't care about it because it's just an ionic compound and it's like a salt of the conjugate base of methanol, which is this. So when you put it in solution, it'll just dissociate. And remember that elimination reactions are different from SN1 or SN2 reactions in that they form a product that has a double bond somewhere. And this is because it has to, this base has to attack a hydrogen that's the opposite stereochemistry to the leaving group. So in this case, we can kind of like see two different possibilities for which hydrogen it can attack. And remember, it has to be trans to the leaving group. So because this bromine is wedged, the hydrogen has to be on an adjacent carbon, so this one or this one, and it has to be dashed. So we can see that there's two possibilities of this. But remember that for these types of elimination reactions, we want to choose the side to put the alkene on where it's going to create a more stable alkene. So in this case, we're going to want to attack this hydrogen on the left side, because although there could be two possible products, because the alkene can either be added here or it can be added here, we want to add it to this left side because there's already a methyl group that is bonded to this carbon. So if we add an alkene here, it's going to be a more stable, more substituted alkene. So that's how we choose which hydrogen to attack. And at this point, this base is going to grab this hydrogen, and then this bond between the hydrogen and the carbon atom that it's bonded to is going to shift over and create a double bond nearby, and then that's going to push the electrons out and make this bromine leave this molecule. So you're going to get something that looks like this. And you're going to get methanol, because remember that this conjugate base of methanol is going to become protonated and it's going to just become methanol. And you also get Br minus as a side product. And just as a note, you can see that the starting material has stereochemistry on this methyl group on the left, whereas the product does not. And that's because that once you remove this hydrogen, there's no longer 4 bonds attached to this carbon. It's going to become an sp2 carbon, not sp3, so we're not going to assign stereochemistry, and that's why this methyl group, as you can see in the product, loses its stereochemistry. So that's going to be our product for this second part, and I'm going to draw it out. That's kind of messy. Oops. There we go. For part B of this problem, it's a similar thing, except instead of having one precursor alkyl halide and then reacting it with 2 different reagents, we're starting with reagents and we're reacting it with 2 different alkyl halides. So I'm going to do the same thing and start from the left side with this tertiary alkyl halide. And we already know that this can be translated to the conjugate base of ethanol, I'm pretty sure. So it's CH3CH2OH, and, I mean, not OH, O minus. And it's a small, relatively small molecule, so we need to keep that in mind as well. So let's start with considering this first, not reagent, alkyl halide that we're reacting this reagent with. And as I stated before, the Na plus is just there as a conjugate, as to form the salt of a conjugate base, which is this. So in the solution, it's just going to leave, and we're not going to care about it because it's ionic. But anyways, we need to first determine what kind of reaction this is going to be. Is it going to be E1, E2, SN1, or SN2? And we already see that this is a tertiary alkyl halide, which is pretty bulky, or it's pretty hindered. So that doesn't work well with SN2 reactions, which prefer primary or secondary or methyl alkyl halides. So we're going to get rid of the SN2, and we know that it has to be between E1 or SN1 or E2. And remember that SN1 and E1 come together because they can't be separated at least for the purposes of this class. And we can narrow it even more down to E2 instead of E1/SN1 because this is a strong base, because it's a negatively charged, and usually negatively charged things are strong nucleophiles or bases. So we know that it's going to be an E2 reaction. And now that we know that it's an E2 reaction, we can draw the mechanism and determine the product. So we're starting off with this conjugate base of ethanol, and we're going to start off with Na plus as well, which we disregard, and we're reacting it with this alkyl halide that looks like this. And because it's an E2 mechanism, we need to know that it's concerted one-step mechanism. And in this case, there's not really a specific hydrogen that is preferred over the other, because these are all like the same substituent groups, and they're all going to have 3 hydrogens bonded to them. And so you can choose either one, like out of the 3. I'm just going to choose this top one, and remember that since there's like 3 hydrogens all bonded to here, sorry, I'm going to move this down. One of them is bound to have the opposite, like, trans stereochemistry compared to this chlorine, which is what's required for elimination reactions. So anyways, this O minus, this base, is going to grab one of these hydrogens, which is going to break this bond between the hydrogen and the carbon in this methyl group, and then the bond will shift over to make an alkene or a double bond. And that's going to put pressure on this chlorine to leave the molecule. And so you're going to get something that looks like this. And you'll get Cl minus as a product, and you'll also get ethanol. But we only really care about this. So that's going to be our product for this first um, reaction with this tertiary uh, alkyl halide. For the second half of part B, we're reacting it with a different alkyl halide, and as you can see, compared to the first one, which was a tertiary alkyl halide, this is a primary alkyl halide because there's this carbon immediately only has one other neighboring carbon. And remember that primary and methyl alkyl halides work well in SN2 reactions, and we also know that it's an SN2 reaction because this reagent is negative, so it's a strong base or nucleophile depending on the alkyl halide involved. So we know that it's going to be SN2 because it's a strong nucleophile indicated by the negative charge. So now that we know that it's an SN2 mechanism, we can go ahead and draw out the mechanism and determine the product of this reaction. So similar to the previous reaction, we're given this conjugate base of ethanol and Na plus ions, and we're reacting it with an alkyl halide. In this case, it's going to be a primary alkyl halide. And like I said before, the Na plus ions don't matter because they're just dissociating from the ionic compound. And it's an SN2 reaction, so this is actually going to be a nucleophile and not a base. So instead of attacking one of these hydrogens that are bonded across from this chlorine, it's going to just attack the carbon that is bonded to the chlorine. And because it's an SN2 mechanism, the leaving group doesn't leave first, it just stays on there. And the pressure from this this nucleophile is going to push it off. So it's going to be a one-step concerted mechanism. And technically, usually SN2 mechanisms result in an inversion of stereochemistry, but we're going to see that it doesn't really matter in this case because this carbon that is bonded to the chlorine doesn't even have stereochemistry to begin with. Because remember that carbon likes to form 4 bonds, and 2 of these bonds are already formed. They already have substituents, but the remaining 2 are just hydrogens. And remember, you can't really assign stereochemistry when 2 of the substituents are the same. So we're just going to ignore stereochemistry, but keep in mind, though, that in general, you want to think of SN2 reactions as something that will invert the stereochemistry of the original molecule. So, anyways, this oxygen that has a negative charge is going to be attracted to this partial positive charge on this carbon that's bonded to the the halogen. So it's going to attack from a side that's not hindered. In this case, it doesn't matter because, like I said, there's no stereochemistry involved. But anyways, this it's going to attack this carbon, and then that's going to break off the chlorine as a leaving group. And you're going to get something that looks like this. And you'll get chlorine as a negative ion as well. And yeah, so there's no stereochemistry because there's 2 of the same substituents, which are hydrogens. So it doesn't really matter. There's no hindrance, but keep in mind that for different problems, it might be different. So whenever you see some halogen like chlorine, bromine, etc., that has a wedge, turn it into a dash after you do the SN2 mechanism, or the other way around. If it's originally dashed, turn it into a wedge. So anyways, this is the product for this part of the problem, and I'm going to draw it in here. For part C of this problem, we're given an alkene starting material and we're reacting it with 2 different sets of reagents. So the first set of reagents is HBr and peroxides, and the second one is just HBr. So I guess we could start with HBr and peroxides. And one thing that we should probably recognize immediately from peroxides is that whenever we see an H bonded to an X, where X is basically any halogen, and we see peroxides or light or heat, that's going to show us that it's an anti-Markovnikov addition, which means that this halogen, the bromine, is going to be added here, where it's added to the less substituted carbon on the side of the alkene. And it's also going to be in radical reaction, which I think is new in this exam compared to the last exam. So I'm going to write that down too. It's going to be a radical reaction, and radical reactions consist of 3 steps: initiation, propagation, and termination. And I'll show you what each of these means. So we're starting off with this alkene starting material, and it's cyclic, and we have one side that's more substituted than the other side. And we're reacting it with HBr and peroxides. And remember that peroxides are just ROOR, where these O's are oxygen atoms and these R's are just like chemical groups in general. It doesn't really matter what they are, but we just represent it as ROOR as just for ease. And initiation is going to go from 0 radicals to 2 radicals, so I'm going to label that here. And in this case, we're going to initiate this reaction by breaking this in half. And a radical is basically just half of a bond, and we're going to represent that by showing 1 electron of a lone pair. And when we show this bond breaking into a radical reaction, we're not going to use an arrow that looks like this. We're going to draw a half arrow like that to showcase that it's only 1/2 of the bond that's being broken. So in this case, we're going to split it down the middle in half, and each of these groups is going to get a radical. So we're going to have 2 RO groups with a radical on the oxygen. And the next thing that's going to happen is it's going to react with the HBr, which is going to split in a similar way, where the hydrogen gets a radical and the bromine gets a radical as well. And in this case, we can kind of group this reaction together as one, because this hydrogen is going to have a radical. It's going to be unstable, and it sees this oxygen that has a radical, which is electronegative and kind of works as a base, so it's going to just react like that. And by the way, this is how you show a radical reaction forming 1 full bond. You just put 2 of these half arrows in the same direction, and that's how you show it. So we're going to end up with ROH, and we're going to have Br, like bromine, with a radical. The next step is propagation, where we go from 1 radical to another radical. So in this case, we just take this precursor starting material, and we kind of bring this bromine over here, and we see that it has half of a possible bond shown by the radical, right? And remember that each bond has 2 possible radicals, and so this alkene is going to break into 2 radicals. So half of it is going to go to this side where it's more substituted, because the radical wants to exist in the more substituted side of the alkene because it'll be more stable. And then the other half of this double bond is going to turn into a radical reaction with this bromine radical, and it's going to form a bond with it. So we're going to get something that looks like this, with the radical on the more substituted side of the carbon, or of the alkene. Then the next thing that's going to happen is, remember, we have a ton of HBr in this solution, or as a reagent, so we're going to bring that back, and we're going to react it to get rid of this radical. Because remember, radicals are just generally not that stable, and so if it's preferable, we're going to try to get rid of them. And the same thing is going to happen that happened here. So this HBr is going to break into 2 parts, and we can just use the radical on the hydrogen as a 1-step reaction, because it's virtually just going to happen in 1 step, because the hydrogen wants to form a bond with another radical. So we're going to get something that looks like this. And we're going to get a bromine radical as well. And this is probably the product they want you to show. And keep in mind that this radical is just disappearing because it's forming a bond with hydrogen. And in a carbon skeleton structure representation, we don't show bonds between carbon and hydrogen. We just assume that they're there. So that's why I didn't show anything here. But that's going to be one of the products that we can have in this reaction. but there's going to be a lot more products, and I'll show you how. So there's this third step called termination, where you go from two radicals and you turn them into no radicals. So you basically get rid of the radicals, and there's multiple ways you can do it. So we already did that once here, where we turn this into this uh, product that has no radicals, but there's also multiple other ways you can do it. So looking back at these previous intermediates we have formed, like for example, we have this one, which I just moved down here, and it's a radical, right? It's not stable. It wants to interact with another radical to form a bond. And we also have this bromine radical, so like one other possible product could be this, where these two radicals form one bond, a full bond, and we can get a product that looks like this. Or I guess another product we can get is we take two of these and we react it together and we get something that looks kind of scary, I guess. It looks kind of weird, but you don't really see these that often. And then you'll get like this weird looking molecule. And I guess a third reaction that could happen is just the bromine radicals react together and just reform something like dibromide. So those are like three possible other products that could arise from this reaction. But since we're starting with this alkene, they're probably looking for something like this. So I'm just gonna write that down as the answer. This is kind of not good. I'm not good at drawing hexagons. Yeah, that is going to be the answer that they're probably looking for this reaction. Although you could technically draw any of these as well, because it just the problem just says draw a product and not the product. For the last part of this problem, we're reacting this alkene starting material with HBr, and remember that without peroxides or light or heat, it's not a radical reaction. It's just a simple um, nucleophile carbocation involved reaction. And it's going to be a Markovnikov reaction. So rather than adding the bromine to the less substituted group, as we've seen here, it's being added to the less substituted side of the alkene. In this case, we're going to expect it to be added to the more substituted side of the alkene. And I'll show you the mechanism as a refresher for why that is. So we're starting off with this same alkene starting material, and we are reacting it with HBr and nothing else. And in this case, the alkene is going to act like a nucleophile and grab onto the hydrogen, which breaks the bond between the H and the bromine. And we're going to have some intermediate that looks like this, where the carbocation is on the more substituted side of the alkene because it's going to be more stable that way. And we're also going to have Br minus as a side product. And in this case, we can check that we did this step correctly because these original two molecules have a net charge of 0 and they're both neutral. And here, these intermediates that we just created are also a net charge of 0 because a 1 plus charge and a 1 minus charge even out to a neutral charge. And in this case, we're not going to rearrange the carbocation in any way because it's already in the most stable position it can be. Because all of these other possible carbons it could be on are secondary carbons. Whereas this one that it's already on is a tertiary carbon and it's just going to be the most stable it can get. So that's going to be where the carbocation just stays there. And the next part of this reaction mechanism is the Br minus ion is just going to come back and attack this carbocation. And we're going to get something that looks like this. And that's why the reaction with just HBr and nothing else is going to result in a Markovnikov addition of bromine. So I'm going to draw that out, and hopefully you remember that from the last exam, but if not, that's okay. That's what this is for. Or propose a mechanism that explains the following reaction. Use curve arrow notation to indicate the movement of electrons. So for this problem, we're also not told whether it's going to be elimination or substitution, but we can tell based on the reagents we're given and the products we're given. So in this case, since we're only given two alkene products, we know it's going to be elimination. So it's going to be either E1 or E2. And technically, if it's going to be E1, it's going to also have SN1 involved, but we can just ignore that since we're not given any products that are alkanes. So we're only going to be dealing with elimination in this case. So the next thing we need to do is determine whether it's E1 or E2 out of the elimination reaction mechanisms. Remember that neutral things are more associated with E1 or SN1, which is not a concerted reaction mechanism. They're both going to involve multiple steps, with the first step being that the leaving group leaves first because the reagent, the base, or the nucleophile is not strong enough to push out the leaving group in one step. And that's because usually negatively charged things are stronger nucleophiles or bases, whereas neutrally charged things are weaker. And in this case, we have a weaker base because it's neutral charge. So because it's a weak base, we're going to know that it's E1 mechanism because an E1 mechanism has multiple steps and it's not the base isn't strong enough to cause the leaving group to leave on its own. So now that we've identified that it's an E1 mechanism, we can draw it out. So we're going to start off with this precursor, this alkyl halide, and we're going to just remove this leaving group first because in an E1 mechanism, the base is not strong enough to cause the leaving group to leave, so it has to leave before the base acts on this molecule. So we're going to get a carbocation intermediate here, and we can recognize this as not the ideal carbocation because, as you can see, this one is the carbon that it's currently on is secondary carbon because it has these two neighboring carbons that it's bonded to. But as you can see, just one bond away, there's a tertiary carbon that it could move onto. Because remember that there's this carbon, and then this methyl group also has a carbon it's bonded to. So in this case, we're going to want to rearrange this carbocation. And remember that it's easier to move a smaller group than a larger group. In this case, this neighboring carbon actually also has a dashed hydrogen behind it because carbon wants to form 4 bonds, and we're given the indication that there's going to be a dashed hydrogen in the back because this methyl group is wedged. So we're going to move this hydrogen over to here, and it's going to replace the carbocation, which is going to move to this carbon on the left. And in this case, we can actually get rid of this wedged stereochemistry because now that the hydrogen has been moved over here, this carbon is going to be sp3 and have 4 substituents, whereas this one does not have the hydrogen anymore. It's going to have an sp2 hybridization, which you cannot assign stereochemistry to because you can only assign stereochemistry when there's 4 substituents to a carbon atom. So we're just going to ignore the stereochemistry for now. And that checks out because, as you can see in the products, it's also not shown that there's stereochemistry on that methyl group. And because there's 2 products that were given, we kind of get the indication that there's 2 possible ways to take this next step. So there's going to be 2 mechanisms after this first step, and I'm going to draw them out. Because we are asked to explain the whole reaction and not just one half of it. So the first possibility is that we have this molecule with the carbocation on this carbon with the methyl group, and the hydrogen that's gonna be reacting with this weak base is on the right side of this carbocation. So in this case, remember that the hydrogen always has to be on the other side compared to this methyl group that the carbocation is involved in. And in this case, the oxygen is going to be electronegative. It's going to grab onto the hydrogen, and then this bond will turn into an alkene. And because the leaving group's already gone, we don't have to do any more pushing out the leaving group. So we're just going to get something that looks like this, which matches up with this first product. The second possible mechanism is just going to be the same thing, except the hydrogen is on the other side of the carbocation. So it's going to be on this left side. And the same thing's going to happen where this base is going to attack, or like it's going to become protonated with this hydrogen. And this bond between the hydrogen and the carbon is going to shift over and create a double bond. So we're going to get something that looks like this, which, as you can see, matches up with the second product that we're given. And just for clarity purposes, I'm going to box these so that it makes more sense. 5. Propose a mechanism for allylic halogenation of the following alkene. Show all elementary steps. Use curved arrow notation to indicate the movement of electrons. Label steps as one of the following types: initiation, propagation, or termination. Note, you only need to provide one example of a termination step. So for this problem, we know that it's going to be a radical reaction because of the presence of UV light. And remember that whenever we see light or heat or peroxides, we're going to know that it's going to involve radicals. And we're also asked to break this down into 3 different steps: initiation, propagation, and termination, and to label them as such. So as you could probably tell from the name, initiation is the first step. And for this problem, initiation will just involve this dibromide breaking into 2 bromine radicals. And then the next step is going to be propagation, where one radical turns into another radical. So there's going to be a radical on each side of this reaction mechanism sort of equation. So on each side of the arrow, you're going to have one radical. And so in this case, we can bring down this starting material, and it has an alkene or a double bond. And we're going to react it with one of these bromine radicals we made in the initiation step. And we want to react it in a way that results in the radical ending up here. We don't want it to end up on this side because vinyl radicals, or radicals that are on carbons with a double bond, are not as stable as allylic radicals, where there's going to be a single bond in between that radical and the carbon that's bonded to a double bond. So we're going to want this radical to end up here on the other side of the arrow. So to do that, we know that there's also going to be 2 hydrogens bonded to this carbon, and we're going to react one of them with this bromine radical. And remember that a radical is basically half of a single bond, so we're going to take 1/2 of this bond, react it with this radical on the bromine, and the other half of this bond between carbon and hydrogen is going to just become a radical on this side, where it's going to be the allylic, more stable preferability of the radical. So we're going to have a radical that looks like this, and we're going to have HBr formed again between this hydrogen and this bromine radical. Then the next step is that we can rearrange this to look nicer, because this is technically already an allylic radical, so it is already pretty stable, but we want to make a product that looks like this. So that involves rearranging it so that the double bond somehow ends up here. So to do that, we can just take one of these radicals, and half of this double bond, it's going to form a bond here, and then this other half of the double bond will just become a radical on this side. So it's going to end up like this. And the radical ends up here because, if you remember, a radical is just half of a bond. So there's already a bond here, and then half of this bond goes here, and the other half is just the radical, so that makes a double bond here. And just keep in mind that, similar to the thing about charges, like net charges, each side of the reaction, like each side of the arrow, should have the same number of double bonds if you're not adding anything else to it. So in this case, we see one double bond, and this on the right side of the arrow, we also see a double bond, so that checks out. So you can use that as a way to check that we did this step right. So now we have the setup to create this product that we're asked to create. And so the next thing we can do is remember that there's tons of dibromides in this solution. There's like trillions of them. So we're gonna just take this rearranged radical that we made, and we're gonna take another dibromide. It's gonna break into two bromine radicals, two of them, and then one of these is gonna react with this radical that's on this cyclic alkene, and we're gonna get a product like this. And this is going to be allylic halogenation because this carbon that bonds to this bromine is one bond away from this double bond. So that's going to be preferable because remember that allyl groups are pretty stable, whereas vinyl groups, so if the bromine was just added here, that would not be stable and it would not be favorable. So this is going to be the product that you're given, but we're also asked to do a termination step. So there's also multiple other products that you can get, even though in this problem it only says you have to provide one example. I'm going to show all of them just so it's more clear. So the first product that could result from this termination is two of these bromine radicals are going to come together and just reform dibromide. The second possible termination is going to be kind of what we have here. I'm just going to redraw it so that it's more clear that it is also a termination step. So this radical that we rearranged is going to react with a bromine radical, and it's going to form this product that we were looking at in the problem. And I'm just going to box these so that they're easier to see. And then the third thing that could happen is two of these rearranged cyclic alkene radicals are going to react together and form some messy looking, weird looking molecule, or that's just how I would describe it. I don't really know how to describe it, but it's going to end up looking something like this. Sorry, I am not good at drawing these. So these are the three possible products you can get from this problem, but we're asked to show the mechanism of just this product, which is given here. So we already did that. These additional termination steps are not required to get points on this problem, but it might help in making more sense of how these steps are differentiated. Because as you can see, in all three of these termination possibilities, it's two radicals coming together to form a product that does not have a radical at all. 6. Propose a multi-step synthesis of one of the following synthetic targets using the following building blocks as the only source of carbon atoms. Circle the synthetic target for which you are proposing a synthetic route. For this problem, the only thing you need to do to get full points is to choose one of these, but I'm just going to show possible ways to synthesize all of them. So let's start with this one on the left. I'm just going to label it number 1. The first thing we should do in these types of problems, if you're not sure what to do, is count the carbons in both the synthetic targets and the building blocks. And that will help us determine which building blocks we want to use to synthesize the desired product. So for this product, we can see that there's 4 carbons, and we can also see that the building blocks, this one has 3 carbons, this one has 2 carbons, this alkyl halide has 2 carbons, and then this is a 5 carbon ring with an extra methyl group on the end of 1 carbon, so that's 6 carbons. And we want to choose building blocks that will add up to the total number of carbons in our synthetic target. So remember, this has 4 carbons, and the only way that any of these can add up to 4 is these two. So we want to use the alkyl halide and this alkyne as our building blocks. So let's start with the alkyne. Remember, there's a reaction with NaNH2, which will deprotonate one side of this alkyne. And the reason why is because this is an ionic compound and it dissociates into Na plus and NH2 minus ions. And this is basically a base. It's an amine, which is basic. And the electronegative nitrogen atom will be attracted to this hydrogen and it's going to break off a bond. And we're going to get something like this, where it's a terminal alkyne. Terminal meaning that the triple bond is on the end of this carbon chain. It's not in the middle of the carbon chain. And this also can act as a nucleophile, and we can react it with the second building block that we identified that might be useful for this reaction. So let's go ahead and do that. Remember that this is negative and this is able to act as a nucleophile, so it can go in and attack this carbon that's bonded to this bromine, and then this will act as a leaving group, and then we'll get an intermediate like this. And now, as you can see, we do have 4 carbons, so that's 1/2 of the reaction. That's 1/2 of the mechanism that we were able to do. And then the next thing is we have to figure out how to get an oxygen in the mix. And to do this, we can probably first think about alcohol reactions. And this is a terminal alkyne. So we have to use the reagents Ca2BH and H2O2 NaOH, because remember that it's a terminal alkyne. In the case of an alkyne that's not terminal, we can just use BH3, but this is a terminal alkyne, so we can't do that. We have to use these 2 reagents. And it's going to do an anti-Markovnikov sort of addition of an alcohol group. So it's going to add the alcohol group to the less substituted side of the alkyne, which is going to be this left side. Because remember that this left side is only bonded to another hydrogen, whereas this right side has it's a primary carbon, or technically secondary. It's gonna have a carbon here and a carbon here that's bonded to. So we're gonna have another intermediate product like this. And just to check that we make that it's correct, if we count the carbons, it should still add up to 4, because nowhere in this reagent are we adding carbon atoms. Remember, all of the carbon atoms have to come from these building blocks. And this is very, very close to our final product that we want. But remember that this is in the enol form, and that's not as stable as the keto form. So it can tautomerize. And to show this, we show this this arrow split in half, with one half of the arrow being longer and then the other half being shorter. And this is because when you're synthesizing this product in like a lab, you're gonna get like 99.99% of the keto version and like very small amounts of the enol version, because it's way less stable than the keto version. And the keto version is just a ketone. It's gonna have a double bonded oxygen to a carbon, and the hydrogen will not be shown because it's a carbon skeleton structure and we don't show hydrogens. So the way to draw the keto tautomer is just to move the double bond to the oxygen, and the hydrogen, we can just kind of ignore it. It's gonna move somewhere else. So we're gonna just draw something like this. And this is our final product for this first synthetic target. For this second synthetic target, we could start off with a similar method where we choose a building block that either resembles the target molecule or has the same number of carbons. So obviously we see a ring here and we see a ring here, so that's pretty obvious compared to like the last problem. So let's start off with that. And I'm just going to draw out the final product and label it as number 2 to make things easier. The first thing we kind of probably want to do with this building block is to add a bromine. And we can do this by doing a radical reaction with dibromide and light or heat. Because if we do this, it's going to be a Markovnikov addition of bromine. So it's going to add a bromine here, and then we're going to be able to transform it later into an alkene, which will allow us to add the alcohol group and the other bromine. So in this case, with light or heat, this dibromide will break up into 2 radicals, and then one of them will react with a hydrogen that is going to be on the more substituted carbon, because remember, we want the most stable radical possible in this entire molecule, which is going to be here, because this carbon is tertiary. The rest of these carbons are all secondary, and then this is methyl. So we want to, or no, this is primary. So we want to react with the hydrogen that is bonded to the more substituted carbon, because then we'll have a more stable radical, which the more substituted carbon it is, the more stable the radical will be. So we're going to react one of these bromines with the hydrogen, and then remember that this half arrow is only half of a bond, so we still have to do something with the other half of the bond. So in this case, like I said before, we can dump the other half of the bond into this carbon, and it'll turn into a radical at this carbon. So we're going to get an intermediate that looks like this, and we'll have HBr and another Br radical as a side product. And now we can just react these together to form the Markovnikov product of this reaction. Now, like I said before, we can see that this is a leaving group, a good leaving group, and across from it, there's a hydrogen that can, there's 2 hydrogens bonded to this carbon that's directly adjacent to it, and this will pave the way for an elimination reaction. So in this case, we want to use a small base like NaOH, which is ionic, and so it's going to actually turn into Na plus and OH minus ions in solution, and we don't really care about the Na plus ions. But it's basically going to act as a base. And remember that the difference between a base and a nucleophile is that a base attacks a hydrogen. So it's a hydrogen acceptor or a proton acceptor, whereas a nucleophile attacks either a carbocation or just a carbon, and that will push the leaving group out. So in this case, NaOH is a base, or more specifically, the OH minus is a base. So this electronegative oxygen will attack the hydrogen, one of these hydrogens, because technically the hydrogen and the bromine have to be trans, but it doesn't really matter because one of these has to be, right? Because there's 2 of the same atoms here, and we're not really shown stereochemistry. But anyways, so this OH minus will attack a hydrogen that's trans to this bromine, which will become a leaving group. And as in return, the hydrogen that the bond between the hydrogen and the carbon will transfer over to make an alkene or double bond, and that's going to push the leaving group out. So we're going to have another intermediate like this. And now it seems kind of clear, right? We can use dibromide and H2O or water to add the alcohol to the more substituted side of the alkene and add the bromine to the less substituted side of the alkene. And this is going to be an anti-addition reaction, which means that they're going to end up trans to each other. So as you can see in the target, in the synthetic target, the alcohol group is dashed, whereas the bromine is wedged. And this is very important. So I'm going to write that out, and I'll draw out the mechanism to show. Actually, let's make this arrow longer. So like just as before, this alkene will act as a nucleophile. It's going to grab onto one of these bromines in a dibromide, and the other one will leave or kind of become a leaving group. So then it's going to look sort of like this, where we want to add the bromine to the less substituted side of the alkene, because then we can add the carbocation to the more substituted side, which is preferable over the other, I guess, possible way you can do this, where it could be like this. But that's not very favorable, because this is a tertiary and more stable carbocation, whereas this one is a secondary and less stable carbocation. So that's important to remember. And also, we have this Br minus as a byproduct, which is important to remember as well. If you ever are stuck or you're not sure if you did the step right in the mechanism, just add the charges of all the participating molecules from one side of the reaction to the other. So in this case, both of these have a net charge of 0, so the total charge is also 0. And in this case, in this right side, it's 1 plus and 1 minus, which also add up to 0. So that's just a good way to check. And you might be tempted to add this back to the carbocation, but don't do that. Instead, this bromine is going to have these lone pairs that's going to be very electronegative, and it's close to this carbocation. So it's going to want to bond to the carbocation. And we'll get another intermediate that looks sort of like a triangular ring shape. And the positive charge will have been transferred over to the bromine. Well, now it's a bromonium ion because it has a positive charge. And now we can bring water into the mix. Water is electronegative, or more specifically, the oxygen atom in water is electronegative, and it's gonna attack either one of these carbons that is bonded to the bromonium ion. But remember that the more substituted carbon has a higher partial positive charge, so that's going to be the preferable way to attack it. So the oxygen will attack this more substituted carbon, and then as a result, this bond between carbon and bromine will break, and we're going to get something that looks like this. Where the positive charge is now transferred over to the oxygen, because oxygen likes to have 2 bonds, but now it has 3. So now that you see that the positive charge on oxygen should be a red flag, we shouldn't end at this product, because obviously neutral charges are more stable than positive or negative charges. So a very easy way to get rid of this positive charge is another reaction with water, because there's tons of water molecules in this solution, like trillions of them probably, and we can just do a simple acid-base reaction where the water or the oxygen in the water molecule acts as a base and accepts one of these hydrogens, which allows this final product to have a neutral charge. And that's our final product. Just I haven't drawn it with stereochemistry, but you should know that it is anti-addition. And as a result, we'll also get H3O plus as a side product. For the third synthetic target, which is this one, we're going to be using the same building block or starting material. As you can see, this building block is cyclic, and this is also cyclic, and it just looks very similar. So that's why we're going to choose that. I'm just going to rewrite it. And similar to the previous problem, we want to consider what kind of steps are we going to take that can get us from this to this. So remember that we can work backwards. So for this particular target, we see that there's 2 alcohol groups added, and remember that there's an alkene reaction that can result in 2 alcohol groups being added to either end of the alkene or the double bond. So we want to go back a step further and determine how are we going to make that alkene. Well, we could start by reacting this starting material with dibromide and light or heat, which will be a radical reaction that will add one of the bromine atoms to the more substituted carbon. So in this case, this will first break into 2 bromine radicals. And remember that we want to form the radical here rather than some other carbons like these 2, because this carbon with the hydrogen that I drew in is a tertiary carbon, which is more stable than these 2, which are secondary carbons. So we want the radical in the most stable position, which is going to be in the more substituted carbon. So now we have these 2 bromine radicals, and we can take one of them and we can react it with this hydrogen. And keep in mind that in a radical reaction, these are all half arrows, which signifies half of a bond. So we still have to do something about this other half of the bond here that's bonded to carbon. And what we can do is we can just draw another half arrow, and it's going to result in a radical on this carbon atom. And we're going to make HBr, and we're still going to have one more bromine radical just floating around that we haven't reacted with yet. And now we can see that we can easily make a termination product, because this is a radical and this is a radical. So we can react these together to form a single bond, because remember that 2 radicals makes 1 bond. And we can see that we get the Markovnikov product from this reaction. Next, we can try to make an alkene out of this, and that will come from an elimination reaction. And actually, there's like 2 possible ways we can do it, because remember that we just have to choose a beta hydrogen that is bonded to a carbon adjacent to this carbon, which is bonded to a bromine. So we could choose a hydrogen from here or a hydrogen from here. And let's just do a little thought experiment to see which one we want to choose. So for this first possibility, if we choose a hydrogen from here, we're going to have an alkene that will look like this. For the second possibility, if we choose the bottom hydrogen, we're going to have an alkene that looks like this. And now you might not know why this is important, but let's take it a step further. If we remember that there's a reaction with, I think it's OSO4 and NaHSO3 and H2O, which will add alcohol groups to either side of the alkene, so on this side and this side, or in this case, on this side and this side. So we're going to see which one of these is going to give us the desired product. And I'm just going to move this over a little bit so there's more space. If we react with this intermediate alkene, we're going to get a product like this, where one of the OH groups comes out from here and one of them comes out from here. And actually, this is the same as this. It's just I drew it the opposite way, but let's just redraw it to make it more clear. There's going to be one alcohol group sticking out of this carbon on the left side of the alkene, and there's going to be one sticking out of the right side. And on this bottom, this other alkene that we could make, possibly, it's going to be the same thing, where the alcohol groups will be on either side of the alkene. And as you can see, this is not the desired alkene, because it won't give us the desired outcome, which is this the 2 alcohol groups coming from the same carbon, with this one having an extra carbon in between. So we want to react with this top hydrogen. So to do that, we could see that this is a tertiary alkyl halide, and in this case, we can either use E1 or E2 reactions, and I'm just going to do an E2 reaction because it's one step, and I think it's just neater and easier to explain. And I'm going to choose a strong, bulky base. In this case, I'm going to choose the potassium salt of tert butoxide, which will actually just, I'm going to write E2. It's just going to dissociate into potassium ions and tert butoxide. Because remember that this is an ionic compound, and in solution, they will just break apart. And in this case, it's an E2 reaction. So this tert butoxide is going to act like a base, not as a nucleophile, as a base. And this oxygen atom, which is very highly electronegative, is going to accept a proton or hydrogen atom. And then this bond will turn into an alkene, which will push this bromine out and make it a leaving group. So we're going to end up with an alkene like this, similar to what we drew before in our hypothetical thought exercise. And now we can go back and just turn this into an alcohol. Sorry, this is not the right alkene. I meant to draw this one. We can change this into this with a reaction with OSO4 and NaHSO3 and water. And we don't have to know the mechanism for this, I think, for this class, but you should know that it's going to add 2 alcohol groups in total, 1 to each side of the alkene. So in this case, we're going to get a result that looks like this, which is our product that we want to make. 7. Predict the major products of the following reactions showing the initial product and the more stable tautomer. So for this problem, all you need to really know is that both of these reagent groups are going to add a single alcohol group to one side of the alkyne. And in this case, just remember that this one will be adding in a Markovnikov fashion, whereas this one will be anti-Markovnikov. So for the first reaction, we're going to get something where the alcohol group is added to the more substituted side of the alkyne, which is going to be here. And then this is the less substituted side. Because remember that this side has 2 carbons bonded directly next to it, whereas this side only has 1, and then the other atom that's bonded is a hydrogen. So for this first reaction, the enol product is going to just be an alcohol group added to the more substituted side. And for the keto product, remember that these half arrows, the first arrow that's going to the right is going to be a lot longer than the one going to the left to show that the keto product is more favorable and more stable. So it means that if you're synthesizing this product, about 99.999% of the product will be in the keto form, whereas only a small amount will be in the enol form. So to draw this in the keto form, you just have to move the double bond to the oxygen and just kind of forget about the hydrogen. It's still there, it's just not going to be shown, because remember that a ketone has a double bonded oxygen. For this second part of this problem, this second reaction, it's anti-Markovnikov addition of an alcohol group, which means that the alcohol group is going to be added to the less substituted side of the alkyne, which is going to be this terminal side. So it's going to look something like this. And similarly, to draw this in the keto formation, you're just going to move the double bond over to the oxygen and just not draw the hydrogen. 8. Briefly, 1 to 2 sentences explain the chemical mechanism by which antioxidants protect us from reactive oxygen species. So reactive oxygen species in this case will just be considered as oxygen species that are radicals. And remember conceptually that radicals are highly reactive and unstable. So antioxidants will help us, will protect us from reactive oxygen species by donating an electron to the radical, and it'll neutralize the radical so that it has a lone pair rather than just a free radical, which is very reactive and can damage tissues and DNA and stuff like that. So antioxidants donate an electron to the radical species, which stabilizes it. 9. Give the major products of the following reactions. Draw all possible stereoisomers. Note, providing mechanisms is not required for full credit, but can be used in assigning partial credit if the correct product is not shown. So for this problem, I'm going to split it into two parts, where I'm going to group these two together because they're very similar mechanisms, and then I'm going to group these two together. So let's start with this first one, H2 in Lindlar's catalyst. This is going to be a syn addition of two hydrogens to either side of this alkyne, so it's going to be reduced to an alkene. And the way we draw something that has syn addition is different from how we would draw something with anti-addition. So for syn addition, we need to keep in mind that both of these hydrogens are added to the same side. So we have to draw the bending accordingly. So for example, for this first reaction, we need to draw the bending like this, because this indicates that there's a hydrogen on the same side. We can't draw the bending to be like this, because then it indicates that the hydrogens are added on opposite sides, which would be anti-addition, which is not the mechanism of action that we get with H2 in Lindlar's catalyst. On the other hand, this reaction with Na and NH3 is going to be anti-addition, so we're just going to draw it the normal way we would draw the bonds, the carbon-carbon bonds bending. So we're going to draw it like this, and remember there's going to be two hydrogens on opposite sides of this double bond. For the second half of this problem, we're also going to be looking at two very similar reactions, or basically they're the same reaction but just happening twice. So for this left side, we're going to be applying one equivalent of dibromide, and on the right, we're going to be using two equivalents of dibromide. So let's start with one equivalent of dibromide. So I'm going to draw out the mechanism because you do need to know this mechanism. You don't need to know the mechanism for this one or this one. I'm just going to write that down. But you do need to know the mechanism of reaction with dibromide or any halogen with two equivalents of it. So for this one equivalent of dibromide, I'm going to draw out this alkyne, and I'm going to represent the dibromide as Br and Br with a line to represent the bond between the two atoms. And as we've seen before with alkene reactions, it's going to be really similar with an alkyne, where the alkyne is going to act like a nucleophile and grab onto one of these bromine atoms, and the other one will leave. And we're going to get an intermediate like this. And it actually doesn't really matter where you place the carbocation versus where you place the bromine, because as you can see, both sides of this original alkyne, so both of these carbons are equally substituted. So it doesn't really matter. And we also have Br minus as a byproduct. And now if you remember, this bromine is going to be very electronegative, so it's going to bond to this carbocation and form something like this. And the positive charge will be transferred onto the bromine, which is now a bromonium ion. And now this negative bromine ion comes back into play. It can either attack this carbon or this carbon, and as we've seen before, there's no, it can attack basically either one of them because they're both equally substituted. In the case that they're not equally substituted, it's going to want to preferentially attack the carbon that is more substituted because it'll have a greater partial positive charge, which it's more attracted to. But in this case, it doesn't really matter, so I'm going to just choose the left one and show you the mechanism. So it's going to attack this carbon, and then this bond between the carbon and the bromonium ion will break. And you're going to get something like this. So this is our final product after one equivalent of Br2. Similarly, for two equivalents of Br2, we're just going to do the same exact reaction, except now it's probably more clear to you because we've seen a lot of this with alkenes. So I'm going to redraw the mechanism here. And this alkene is going to once again act like a nucleophile. It's going to grab one of the bromines and the other one will leave. And we're going to get an intermediate that looks like this. Where one side of this alkene will be, we're going to add a bromine bond to it, and the other one is going to have a carbocation. And now this additional bromine that we added is going to also form this triangular bromonium ion. And just to remember, we have this Br minus that we also created from the leaving group. And we're going to get something that looks like this. Where the positive charge is now from the transferred from the carbocation onto the bromonium ion. And now this Br minus is going to come back into play, and it's going to attack the more substituted carbon because that has a greater partial positive charge. But in this case, once again, all of them are equally substituted because this carbon and this carbon, they both have two carbons directly next to them. So it doesn't matter which one you attack. And once again, I'm just going to attack the left side because I chose the left side last time and it's just easier to show. So once we attack this carbon, this bond between carbon and bromine will break, and we're going to get a final product that looks like this. This is going to be our product after two equivalents of Br2. It's just the same reaction mechanism, just applied twice. Bonus question 1. Sulfur mustards are chemical warfare agents that react with water to generate HCl at a much faster rate than chloroalkanes without sulfur. Provide an arrow pushing mechanism to account for the formation of HCl or hydrochloric acid from the starting material shown below. So in this problem, we're concentrating mostly on the formation of HCl. So we're trying to create a mechanism or show a mechanism that's going to form HCl. We don't really care specifically about these other products, but they might be useful for us to understand how the mechanism works. So in this case, this is going to be an internal SN2 mechanism because remember that sulfur is a very electronegative atom. So it's going to attack this carbon that's bonded to one of the chlorines. And it actually doesn't matter whether you choose this left carbon or this right carbon because it's a symmetrical molecule and there's no preference for it. So anyways, after the sulfur attacks the carbon, this carbon bond with chlorine will break and the chlorine will become a leaving group. And we'll get an intermediate that looks like this, where the positive charge is now on sulfur because it has 3 bonds rather than 2, and the chlorine will have a negative charge. And we can check that we did this correctly because, as you can see, the only molecule participating in this reaction, or this first step of the reaction, is this sulfur mustard, right? And this sulfur mustard has a net charge of 0, or it's a neutral molecule. And it breaks into these two molecules, or atoms, I guess, and these are 1 plus and 1 minus charge, which also add up to 0, or a neutral charge. So we're gonna ignore this for now, but it's gonna come back later. And now we can think about the role that water plays in this reaction. Water is a good nucleophile. Well, in this case, it is a good nucleophile because the oxygen atom is pretty electronegative, so it can attack one of these carbons to break this bond between carbon and sulfur and break the ring. And in this case, we're going to get an intermediate like this, where the positive charge has now been transferred over to the oxygen in the water. And again, we can check to make sure we did this step correctly, because this negative chlorine ion is not participating in this step, right? So the only two molecules participating in this second step is the neutral water and this mustard intermediate that is positive, or has a 1 plus charge. And as you can see on the other side of the equation, we also have a total charge of 1 plus, which is good because we want to make sure it's the same charge as all of the precursor molecules involved in the reaction. So now we can bring back this Cl minus, because remember, we're trying to form HCl. We're not trying to form H3O plus, which I guess we could form if we took another water molecule and used it as a base to accept one of these hydrogens. But we're looking specifically for HCl, so we're not going to use another water molecule. We're just going to use this Cl minus leaving group that we got earlier, and it's going to act as a base and accept one of these hydrogen atoms, which will break the bond between the oxygen and the hydrogen and neutralize it into an alcohol. So we're going to get something like this, and we're also going to get HCl as a product. So we're going to get an alcohol and HCl, or hydrochloric acid. But we're mainly focusing on HCl, so I just boxed HCl to show that this mechanism does indeed form HCl. Bonus question 2. You are investigating a new nucleophile that you are unsure about how strong of a nucleophile it is. Describe one experimental observation that you could use to determine whether the following reaction proceeds via SN1 or SN2 mechanism. So this is a problem that recalls your understanding of the concept of SN1 versus SN2 mechanisms. And we're not given the nucleophile, so we're just determining whether it's going to be SN1 or SN2 based on testing the product. So if we allow this reaction to occur without knowing what the nucleophile is, what's going to be what kind of properties will the product have that's going to determine whether it's SN1 or SN2? So if you remember, for SN1 reactions, we're going to get an scrambling of stereochemistry, because remember that in SN1 reactions, it's a multiple step reaction, not a one-step concerted reaction. So the first thing that's going to happen is this bromine is going to leave as a leaving group, and we're going to get a carbocation intermediate. And this carbocation is not hindered on either side of it, so we can add the nucleophile to either side of it, and we're going to get scrambling of the product. So it's going to get something like this. Whereas in an SN2 reaction, it's a one-step concerted mechanism. So rather than the leaving group leaving first, the nucleophile will simply attack the carbon from the less hindered side, and then the leaving group will leave. And because it has to attack from the less hindered side, since the leaving group is still bonded to the carbon when it reacts, it's going to not scramble. It's going to give us an inversion of stereochemistry like this. So this is pretty important because this is the main way we can test to determine whether the reaction will proceed via an SN1 or SN2 mechanism. So for SN1, we get scrambling of stereochemistry. And for SN2, as I've shown, we will not get scrambling, we will get inversion of stereochemistry. And the way we would test this in the lab is just test for the optical rotation, because stereoisomers have different optical rotation. I'm pretty sure it's like the same magnitude, but it's opposite directions. So that's how we can determine if it's scrambled or inverted.